Welcome to my presentation on the birthday paradox and autosomal DNA projects. My name is Wesley Johnston, and I'm really excited to show you how you can have a lot more success with an autosomal DNA project than you might expect. I will show you the mathematical basis for the reality that you can have far more success with an autosomal DNA project with far fewer DNA testers than you might expect. This is the result of 10 years of working on autosomal DNA projects and asking questions over and over during that time that I have gradually been able to answer. The bottom line is that there is real power in numbers when working on an autosomal DNA project, and that is what I want to share with you today. I want to start out by making sure that you understand who cannot benefit and who can benefit from this presentation. If you are not willing to participate in an autosomal DNA project and want to do your work on your own, you cannot reap the benefits of the power of a project that brings together multiple kits for analysis of all the different ways that the kits can work together. There is no power of numbers when the number is 1. Collaboration, capital letter, collaboration of multiple testers working together as a group is the key to realizing the benefits of an autosomal DNA project. And for those who do participate in autosomal DNA projects, I will give you the bottom line now. It is possible to have success finding matching pairs of kits in your project with far fewer kits than you probably would think you would need. First, a bit about me. I started out in mathematics. I retired from a long career, computer programmer, systems analyst, database analyst, and finally retired as a senior information disciplines analyst in Chevron's math modeling group. At Chevron, I also headed the company-wide information-based modeling network, presenting all-day seminars by leaders in fields at or beyond the horizon. The nature of the work that I did there was basically to solve the problems that PhD geologists or petroleum engineers or others could not solve with the technology in their own fields, and so they came to the math modeling group and dropped it in our laps and said, solve it. So that's the kind of work that I was doing. After retiring, I indulged my interest in history, having long before earned a second master's degree in history. In addition to family history, I am intensively committed to World War II history with an emphasis on finding and identifying the more than 80 still unaccounted men of my father's 7th Armored Division to bring World War II to an end for their families. This presentation is about autosomal DNA, but at a meta level. But you do need to know the basics of autosomal DNA inheritance. If you tested at Ancestry or 23andMe or MyHeritage or did the Family Finder test at Family Tree DNA, you did an autosomal DNA test. If you've uploaded your GEDmatch, your results to GEDmatch, those were your autosomal DNA results. Your autosomal DNA is in your 22 pairs of chromosomes other than your sex chromosomes. You receive half of your autosomal DNA from dad and half from mom. And they inherited theirs in the same way. So you have about 25% of your DNA from each of your 4 grandparents and about 12.5% from each of your 8 first great-grandparents. The more autosomal DNA that you share with someone, the closer your relationship. This chart gives the average percentage of DNA that you share with a specific relative. You can see that even a second cousin shares, on average, only 3.125% of their DNA with you and you with them. You and a second cousin share the same first great-grandparents, but which one of your 8 first great-grandparents was the one, and which one of your match's 8 first great-grandparents was the one from whom both of you inherited that shared 3.125% of your DNA. Or maybe it's a shared couple. Figuring out the common ancestor in autosomal DNA matches can be hard work, really hard work, and very challenging to make sure that you do it accurately. It is important to understand what DNA results really are. All too often, people show their colored maps or ethnicity percentages and say that these are their DNA results. So let's be clear about what are and are not DNA results. Colored maps and ethnicity estimates are not DNA results. They are an interpretation of DNA results, an attempt to read the actual DNA results and say something about them, about your ethnicity. DNA results are the A, C, G, and T base pairs detected at each tested location on your chromosomes. Anything else that is concluded based on these results is an interpretation of your DNA results and not the DNA results themselves. My journey in DNA began the same as all of us. I have these results, but what do I do with them? Finding a robust project with an innovative project leader made all the difference for me. This began with a Y-DNA project administered by Wesley Johnston. After several years of seeing how to do things with Y-DNA, I decided to augment the project by starting a GEDmatch multiple kit analysis tag group for the Johnston Y-DNA testers. I also began autosomal DNA projects of other ancestral lines for relatives who had tested and uploaded to GEDmatch, where I started tag groups for each project. I soon realized that different descendants of the same ancestor had some unique part of that ancestor's DNA that most of the other testers had not inherited. This allowed me to not only find more people who descended from the same ancestor and their family, but also allowed us to begin to piece together the DNA of the ancestor. For example, you might have 4 descendants, but the DNA that each person inherited from the common ancestor was not the same. So you wind up with something like the Tinker Toy structure in the picture. All of these people descend from the same ancestor, but you will not find any DNA that the top 2 testers in the Tinker Toy house share with the bottom 4. Nevertheless, each one has inherited 3 pieces of the ancestor's DNA. This is a key point where autosomal DNA projects have power that a lone researcher does not have. Once you let go of the need to have only people who connect directly to your DNA, you can learn a great deal in an autosomal DNA project. You cannot expect every descendant to share DNA with you. What I also realized was that we were effectively reconstructing pieces of the ancestor's DNA as if the ancestor had been able to do their own DNA test. And as I worked with different projects, I realized that there was a critical mass, as I called it, in one of those projects of DNA tested descendants of a woman born in the late 1800s. And the critical mass, which came about when it suddenly became much easier to bring new kits into the tag group, seemed to be at about 7 kits in the project. Once we had 7 kits, we were quickly able to find a lot more people who matched us. This had not been possible before we had this critical mass. GEDmatch's multi-kit analysis tag groups provided a powerful tool for each project's analysis of an increasingly large number of kits. Several of the projects I work on now have more than 100 descendants or potential descendants of the common ancestor. One has almost 200 kits. With just one click, I can see how the DNA-based estimates show that all 200 of these kits relate to each other or not. With one more click, I can see how the first person in the tag group triangulates with all 200 of those carefully chosen kits in the tag group. I can use the GEDmatch ICW, which means in common with. I can use the GEDmatch ICW tool, which has the unwieldy title of people who match both or one of two kits, to identify people who match both of two of our kits. I can then create a GEDmatch tag group that includes all those matches. I can then use the GEDmatch triangulation tool just within the tag group. And I can use the generations matrix tool just within the tag group, only those kits in the tag group that have been carefully chosen, in order to identify those who descend from the same ancestor and narrow the tag groups down to just those kits. So I establish a core group of kits and verify these by traditional genealogy using family trees supported by solid documentation, and then I expand out from that. If we find a potential new match, I can quickly add that new match's kit to the tag group and make it the reference kit, the first kit in the tag group. I can then run the GEDmatch triangulation tool to see if the new person triangulates with any of those in our tag group and how strong each triangulation is. I can also run the generation matrix just for those kits within the tag group to see how people are related to each other within the tag group and where we have clusters. The generation matrix shown here very quickly tells us how the new kit, the one at the top left, matches to 102 other kits in this particular tag group, and also how every one of the 103 kits in the tag group match or do not match with each other. This new kit and the green and yellow cells tell us that the new kit does indeed closely match with some of our tag group kits. This particular tag group is of known and reputed descendants and descendants of relatives of a couple who married in 1649. Each of the clusters that you see on the diagonal are clusters of families of different descendants who have done DNA tests. So within minutes of having the new kit, GEDmatch ID, I have done a deep comparison with all 102 kits already in this carefully selected tag group. This is why GEDmatch's multiple kit analysis is so important to our project research. And now I'll show you the first steps of how I wound up with the birthday paradox. I realized that the critical mass of just 7 kits in one project identified multiple regions of the ancestor's DNA. We were then able to expand our tag group by using the GEDmatch segment search tool to find other people who match our kits on the same region of the ancestor's DNA. We then sought out the documentation to verify the connection that the DNA had strongly suggested. And we quickly went from 7 kits to about 30 or 40. So I began to wonder just how much is possible with autosomal DNA projects. Recognizing this critical mass aspect of autosomal DNA projects is what started me wondering, what is the critical mass for more distant relationships? What is the limit of how many kits we could have in a GEDmatch tag group? I think the answer is 500, but we are so far only at about 200 on the largest group. And finally, the big question, is there a way to mathematically calculate how many descendant kits I need to guarantee that at least one pair of them share DNA from their common ancestor for specific distances of their relationship? That big mathematical question reminded me of a classic statistical reality that befuddles most people. It is called the birthday paradox. If you have 23 people gathered together, what are the odds that 2 of them will have the same birth day and month? There are 365 days in a year, and 23 is only 6% of 365. So most people think that the odds are quite low that 2 of the 23 people will share the same birthday. In fact, the reality, provable by math and often verified in classrooms where teachers poll their students to show that it really is true, the reality is that the odds are about even. They're about 50-50, that of the 23 people, at least 2 of them will share the same birthday. And this had a lot of resonance with what I was looking at with autosomal DNA projects. The key to understanding the birthday paradox is that we are looking for any pair of people who share the same birthday. And 23 people can be compared with each other in 253 ways, which is more than half the number of days in a year. The math is more complicated than that, but the essence of how the birthday paradox works is that it is considering pairs of people and not just individuals. This chart shows how the number of pairs increases much faster than the number of people. 2 people can be paired in only one way, but 5 people can be paired in 10 ways, and 12 people can be paired in 66 ways. So going from 2 to 12 people is 6 times more people, but 66 times more pairs. There is a simple formula to see how many pairs any number of people have. Multiply the number of people by 1 less and then divide by 2. So 12 times 11 is 132, with half of which is the 66 that you see in the circle. There is a formula for figuring out the probability of any number of people having at least one pair who share the same birthday. If you want to have a 99% probability of having 2 people share the same birthday, you simply use 99% instead of 50% in the formula. The same formula that you can use to calculate how many people you will need for at least 2 of them to share the same birthday with 99% probability also works for figuring out how many DNA tested descendants of the same ancestor you need to have 99% probability that at least 2 of them will match on DNA inherited from that ancestor. What you need to be able to do this is the probability that 2 cousins will share at least 7 centimorgans of detectable DNA inherited from the same ancestor at the different levels of cousins. And the ISOG Wiki Cousin Statistics webpage provides those numbers from 23andMe, Ancestry DNA, and Family Tree DNA. The worst case, the one with the lowest estimated probabilities, is 23andMe. So I chose the 23andMe probabilities for my analysis. I am well aware that some people will argue that it is impossible to go beyond a certain cousin level with autosomal DNA matching, so that looking at 8th or 10th cousins is impossible, according to them. But this presentation is not about that issue. Either you accept 23andMe's probabilities or you do not. But if you accept them, then the calculations that follow are mathematically sound and deterministic. I plugged in the 23andMe probabilities into the formula and did the calculations to see what number of kits I needed at each level for a 99% probability that at least 2 of them would match at each cousin level. The results are that you need far fewer kits than you would expect, just the same as you need far fewer people for the birthday paradox than most people would expect. In fact, the results echoed what I had seen when I recognized that there was a critical mass after which my autosomal DNA projects became easier to expand. I'm not going to go into the details of the math in this presentation. If you want to see those, you can find them in my paper in the Journal of One-Name Studies, which is in the handout. The link is in the handout. What I will show you in this presentation is just what they mean for the success of an autosomal DNA project. What is important in this presentation is just what the paradox means for the success of an autosomal DNA project. But for those who are curious, I'll give a couple of slides to show how the math works, first for the birthday paradox and then for autosomal DNA matches. The probability in the birthday paradox is calculated by figuring out the probability of 2 people not having the same birthday and then subtracting that from 100%. The probability of 2 people not having the same birthday is 364 out of the 365 days in the year, or 99.7% probability that they will not share the same birthday. Each pair has the same 364 out of 365 probability. So we multiply all those paired probabilities together and subtract from 1. If you want to know how many people that we need in order to assure 99% probability of at least one matching pair that have the same birthday, then we set the probability 99% in the equation and we solve for n. With the autosomal DNA matching, we again need to know the probability of 2 cousins matching or not matching. This probability takes the place of the 364 out of 365 in the formula. Everything else is the same. So the 23andMe table tells us that 2 fourth cousins have a 45.9% probability of a detectable shared DNA match being found. But we want the opposite. We want the probability that no detectable shared DNA will be found. So we subtract from 100%, and this tells us that we need to enter 54.1% into the equation in place of the 364 out of 365. So we put that in the equation, and on the left side, we say that we want 99% probability of at least one pair of testers who will match, and we solve the equation. I actually solve the equation first for the number of pairs needed, and then I see how many kits are needed to assure that number of pairs. And for fourth cousins, we find that 8 pairs are needed. So we need 4 kits. 4 kits will actually make 12 pairs, but 3 kits will only make 6 pairs. So the answer for our autosomal DNA project is that at least 4 fourth cousin testers are needed to have 99% probability that at least one pair of them will share detectable DNA from their common ancestor their fifth great grandparents. The results are extremely good for autosomal DNA projects. That's the bottom line. You need far fewer kits than you might expect. For example, for the fifth cousins, who are 6 generations away from their most recent common ancestor, so that they have very small pieces of shared DNA, you only need 29 pairs, and thus only 9 people, 9 testers, in order to have a 99% probability that at least 2 of them will match on DNA inherited from that common ancestor. This is very much in line with what I had called the critical mass. The fact that in some projects we now have about 200 kits means that even a match of 8th or 9th cousins is 99% likely for at least one pair of them. Here again is the Tinker Toy model of what an autosomal DNA project can build. The reality is that as you have more descendants who have tested, you can find more of the regions of the DNA of the shared ancestor. Just because you yourself might not match someone, the reality that one of your matches does match that other person on DNA from the ancestor of all 3 of you lets you build this structure. Ancestry DNA recognized this with their now abandoned DNA circles. Segment analysis and GEDmatch gives us a powerful way to do this with our tag group. But you can see the beginnings of it even on Ancestry DNA where there is no segment analysis. You can start to put together such a structure from Ancestry DNA matches. But without segment analysis of an entire group, Ancestry DNA can only go so far. It basically gives you some pieces that you might be able to put together, but you can't generate this kind of a structure, especially when you go further back. But without segment analysis of an entire group, Ancestry DNA can only go so far. GEDmatch tag groups provide the power that you need to go much further in your analysis with tag groups of larger numbers of kits. This is what the Ancestry DNA circles looked like. If this looks a bit familiar, it is, because here is the image I showed earlier of how 12 people make up 66 pairs. And the Ancestry DNA circles is basically the same thing. Any presentation on autosomal DNA has to alert you to some important caveats. It's all too easy with autosomal DNA to come to false conclusions. The most important caveat of all is that autosomal DNA alone cannot prove a relationship. You need sound family trees and maybe Y-DNA or mitochondrial DNA or any other form of evidence. But the autosomal DNA can point you in a direction, but it can't prove it. Confirmation bias is when you have a preconceived notion and either ignore contrary evidence or stop searching for other possibilities once you find any evidence of what you expected or hoped to find. So if you find some evidence that your match may be connected on the line of your Robert Harrison, born in 1803, it is a big mistake to stop searching. You have to consider all possible ancestral matches, all of your lines, all of your matches lines, and you have to make sure that there are no other lines on which you might match, and not just this one, or maybe not even this one. For example, the DNA that you share could actually have come from an as yet undiscovered ancestor, or from another ancestor who lived in the same area. The further back you go, the more lines you have to consider. And the further back you go, the greater the chances are that some of your lines will not yet be known. So it does take hard work to make sure you have not fallen under the spell of confirmation bias. But when used along with robust family trees and possibly also the use of Y-DNA or mitochondrial DNA or X chromosome DNA, it may be possible to verify that two people who match at that level really do descend from a specific common ancestor that far back. With extreme care for accuracy, highly experienced genetic genealogists have achieved what was once thought impossible with autosomal DNA. As I said in my caveat, they have used autosomal DNA along with other sound evidence to achieve this because autosomal DNA alone cannot prove relationships. Dr. Tim Jansen, one of the pioneers in genetic genealogy, continues breaking new research paths. At the 2020 Institute for Genetic Genealogy, he gave his first presentation of tracing ancestral lines in the 1700s with DNA, which can be viewed in two parts from his RootsTech 2021 presentation. He was able to drop comparison thresholds to 5 centimorgans because he had multiple DNA testers and knew how to evaluate the results safely at that threshold. Martin McDowell heads the North of Ireland Family History Society's Ballycarry DNA project. They have tested many of those living in Ballycarry whose grandparents lived there. This has enabled them to build up a robust DNA database as well as robust family trees. But the records only go back so far and often omit the maiden names of wives. Thanks to what they have learned from the DNA results, they have been able to determine the maiden names of wives born in the 1700s. This sort of cutting-edge work is not for the novice, who is very likely to reach false conclusions by not taking extreme care to handle such situations. A common factor in both of these successful uses is the use of autosomal DNA projects with multiple kits focused on carefully selected kits. And another factor, a critical factor, is that they have taken extreme care for accuracy. So it is possible, but also a great deal of very careful work so that you will not see a lot of presentations of such work. So it is kind of undercutting itself because it's so hard to do that you're not going to see many cases of it. The scarcity of such presentations or publications is a result of the great deal of work required. So it's worth paying attention to these when they are presented. The bottom line is that low probability does not mean no probability. If you have enough testers who descend from an ancestor, your autosomal DNA project can succeed. And thanks to the same mathematical reality that enables the birthday paradox, we now know that the autosomal DNA projects can succeed with far fewer testers than most people would think possible. And that is my presentation. I hope that those of you already working on autosomal DNA projects take heart from this. There is a whole lot more possibility out there than you realized. And I hope that those of you not yet participating in an autosomal DNA project will either find one or start one. Collaboration is the key. The power of numbers is very important in an autosomal DNA project. It is how you offset the odds for two random descendants matching. When it is just you looking for a distant match, your odds are very low. But when you have enough people working together, success becomes much more likely, and you need far fewer people than you might expect.